Okay, so the course will be basically on these three topics. One is quantum field theory. Okay, and then its application to particle physics. And to understand these two topics, what we require the information about the symmetries. So to understand the symmetry, we need to learn something about the this thing. Okay. So the primary aim of this course is mostly for the PhD students who are working in the particle physics mostly. So that's why the applications and all those things that I'll be discussing in the context of particle physics only. Okay. And this theory, you can understand the very vast subject. We cannot cover the whole and every aspect of this theory. Rather, what we can do, we can learn bits and pieces of this theory and mostly the working knowledge rather than the abstract notion of the group theory, such that we can understand the quantum field theory in a better way. And also, in the particle physics, there are a lot of phenomena we'll discuss, and to understand them, the symmetry information of the and the framework of the systems are very important. For example, symmetry breaking and all those things. And mostly the group theory understands, then instead of having a abstract notion, we'll talk about more like this presentation. And from this, it is, I hope, clear that why do you need this? Because particle physics, we deal with different kind of subatomic particles, like electron, the fundamental particles we're talking about mostly, peaks and all those things, find your spin 0 object and spin 1 object, the gauge bosons. So to understand their interactions, you need to first understand how do they transform, and that will be defeated by their representations theory. Okay. So that is the outline of this lecture. So here I thought to start the lecture from every Saturday from 11 a.m. to 1 p.m. But now I came to know that I have few more lectures left for in IIT Kanpur. So that may be shifted in the afternoon, 3 to 5 or 3:30 to 5:30. I'll notify that over the news. So let's start this quantum field. But now, before jumping into this topic, quantum field theory, let us try to understand why quantum field theory, and then we'll slowly understand what is quantum field theory. Now, if you remove this word field as of now, so we have this notion of this quantum theory. Right? And that we have already done in our quantum mechanics course. Now, what was quantum mechanics all about? Certainly, a new theory over this notion of this classical mechanics, where at some particular length scale and the microscopic world, when the classical mechanics fails to describe the phenomenon, we need to incorporate this quantum mechanics. But then something has happened that we cannot rely on quantum mechanics anymore. For example, there are two things which are important in quantum mechanics. Like quantum describes the one particle system, and also it is in non-relativistic nature. Now, if the particles of the states are basically transforming in a relativistic way, we cannot use this quantum mechanics. So that's why the evolution of quantum mechanics is there, and you start with the relativistic quantum mechanics. But if you note carefully, relativistic quantum mechanics, it's not itself a complete and consistent theory. Rather, you will find out this as a bridge from going from quantum mechanics to quantum field theory. Another shortcoming of quantum mechanics is that it describes with a one particle space, and the number of particles are basically on the constant. Yes, sir. Yes, do you have a question?
No, sir. Like I was telling, your audio is somewhat like cracking and it's inaudible and
Is it
you're
true
not.
for all of? Is it true for all of them?
I think so. So because they're writing in
Okay,
chat box also.
okay. Because it depends on sometimes the network connection also. Let me check. Is it better now? Okay. So I can get some positive responses. So I believe I am audible better now. Thank you. Well, so what I was saying that this is more like a bridge from going from quantum mechanics to this quantum field theory. And another important shortcoming of the quantum mechanics is that it doesn't explain the phenomena where the number of particles is not conserved. But those kind of things we have observed in nature. For example, you can think of like electron and positron, they annihilate and then give you a photon. Or a photon, from a photon you get a pair of electrons, right? So this kind of phenomena where the number of particles is not conserved, that cannot be described by the quantum mechanics. So that's why we need to incorporate some theory which is more like a many body theory. And in this actually led the path for this quantum field theory. But that doesn't mean that the construction of this quantum field theory will be completely randomized, right? So what we do, we use the concept of quantum theories and try to build our quantum field theory on that by upgrading status of the which we call the coordinates earlier will give the status of a quantum field associated with that. And if you remember in quantum mechanics, the quantum states, they were not the operators. They are the vectors in that vector space. But here we'll upgrade them and we'll give them the status of a operator. So that is one of the important change from starting from quantum mechanics to quantum field theory. And we'll see how those quantum fields and all those things are there. And whenever there's a quantum theory, the most important questions is about the quantizations. So like in quantum mechanics, we have done, the XP commutator is IH bar. So that is the quantization. But here, we X and there the X and P were the operators, right? But now, as I have mentioned, we'll give the status of the operators to those quantum fields. So we should be able to write down the quantizations in the context of this in terms of the quantum fields. And that's where we'll do the quantizations, and that's what is called the second quantizations. Okay. And this is not the regular Hilbert space kind of thing where we have quantum mechanics is defined. Rather, there's a different vector space which is called the Fock space. But without going into detail, let's try to see that what are the ingredients of these quantizations. So there are many ways to quantize your theory. Most historically famous ones are basically canonical quantizations, and then either you think about the path integral method, or which is sometimes called the functional method diagram. In this particular set of lectures, we'll do these canonical quantizations. Okay. Now, the first question that is asked here is, what do you mean by the canonical? Because in quantum mechanics also, the quantizations when we talk about is the canonical quantizations. Now, if you think about what was my Hamiltonian, because Hamiltonian H is basically function of your, generalized coordinates and generalized momentums in this particular way. And if you note carefully that this qi dot and qi are treated independently, that means qi dot is not treated or derived from the time derivative of qi. That's why your phase space, when you talk about in the Hamiltonian, right? Your phase space dimension is basically how many qi and how many qi dots are there that you have to define. So these are two called the canonically conjugate variables. So they are the canonically conjugate variables. And when you write down the quantization in terms of these canonical conjugate variables, that's why it's called the canonical quantizations. Now, if we think about, the Schrodinger's equation, what was my Schrodinger's equation? If you try to recall the time-dependent one, we have this psi of t, and there we have Hamiltonian, which is basically, let's say, Q1 minus I delta Q1 acting on psi t. Right? So this is the Hamiltonian, basically a function of it, these coordinates and the momentums. So now, what was my psi t? This was the state vector, right? And then we can calculate the any probability and all those things in a quantum mechanical way. And it's very well known to all of us now. But there's another prescription which is called the Heisenberg picture. And what was the distinction, quality from the Schrodinger's one? Because Schrodinger's case, so we call it, let's say, HP in a short form, and let's see. And the Schrodinger picture. So we have a Schrodinger picture, which is called this. Okay. Now, in HP, you basically have the operators, and that actually evolve with respect to time. Okay. In Schrodinger picture, you have the states, okay, that actually evolve with respect to the time t. In between, there is something also exists, which is called the interaction picture. Here, then IP, if you see, the operator and the state both evolve with respect to time, but we have to be careful now, because the name from the interaction, I hope it is clear that when you write down the Hamiltonian, that you should be able to write down in this particular form, where H naught you call as a P part, and this V is called your interaction. Okay. So then we'll see, we'll come back to this thing when we talk about the time evolutions and the Dyson's and all those things, that the evolution is basically sorting that picture when you do with respect to the complete age. But in interaction picture, your H naught and V play independent and different roles in these time evolutions, right? Okay. So now we have to understand that when these evolutions and all those things we are talking about, then we should be able to find out some kind of a canonical equations. So in classical mechanics, if you recall, then we'll find out some kind of Lagrangian equations, okay? And then we'll see that whether if we find out something called the canonical equations, are they related to these Lagrangian equations or not? So now how to understand that? So let's start with some function f, which is a function of q and t. And now my equation of motion of del f by del pr is written as a commutator of this quantity, and then del f by del qr is minus by this p. And then from the Hamilton physical quantities, as you know, the evolutions are related with the commutator of the Hamiltonian. So we have also this set of relations, dqr dt as I h q function of t, and then you have a dpr dt, which is related to I h pr of t. Right? So now, if you make this kind of equivalence with these definitions and these definitions, what you can say that del h by del pr is related to dqr dt and minus del h by del qr is dpr. And this we have already noticed in the classical mechanism. So far, there is nothing we have introduced which is completely quantum mechanical, right? So now we can write down the total Lagrangian or the action if you write down. So I'll write down L0 T1 dt the Lagrangian in a function of Q1 dot. Okay. So this is your action. So I'm not elaborating these things in great detail because I believe all of you have the notion of this knowledge of this classical mechanics, right? Because that I assume to be a prerequisite classical mechanics, quantum mechanics for this course. So now if we take the variations and if we use the boundary conditions that at both ends they vanish, then from there we get these equations ddt of del L del QR dot minus del L del QR equal to 0. And this is what you call the Euler-Lagrangian equations. Now, there are two key points here. That here I'm assuming the Lagrangian is dependent on the function of the QR and QR dot. Okay, but it is not always guaranteed to have this kind of dependencies. It may have some higher derivative of Q. For example, Q double dot, Q triple dot, and so on. And then automatically that will modify this Euler-Lagrangian equations. But for the sake of at least the primary part of this course, we will not consider anything which will violate this assumption. So this will be our working Euler-Lagrangian equation. But you should keep in mind that this is not the generic one. You can extend this and generalize this Euler-Lagrangian equation. And second point, here you have a QR dot and defining from the Lagrangian. And also previously, if you see where I was defining this Hamiltonian, right? This Hamiltonian also has a Q dot. But there's a great difference between this Q dot. When you talk about the Q dot from the Lagrangian, there you define QR dot as limit epsilon tends to 0, q of t plus epsilon minus q of t by epsilon. That is the first principle of the derivative. Now, why is important? This tells you that q are dot, they are not actually independent and then QR. It is a derived quantity from QR, right? Which actually not the case. Uh, uh, this is not the case for the Hamiltonian. Now, why it is important to mention? Because when we talk about the Hamiltonian, then there's a QR function of t and then QR dot function of t. So if you see, if you think when you talk about the time evolution, it will be more clear that if you know a trajectory of this evolution and you break this into a time slices, okay, this is a t0 and this is the final t, okay, then at every time slice, if you see the QR and QR dot, they are defined there. That means they are on the same footing. And if you consider that each time slices are like a clock, so then here only one clock is associated with this Q and Q dot, right? And that's why we do not worry about later when you talk about the time ordering and all those quantities. But now think about the Lagrangian. So Lagrangian, when you define this QR and QR dot, so this QR dot is defined in this way. Now in this definition, you can see that you have a QR at t and then QR at t plus epsilon. Certainly there's a two clocks at time coordinates, or the two clocks are involved. That's why when you describe the quantizations later, whether it's a path integral quantization or canonical quantizations, in terms of the Lagrangian, which is our preferred one, we have to be careful about the time ordering. Okay, so that's why the time ordering is important. Another important aspect that you may notice already, that when I'm talking about the quantizations, I'm talking about the Q and Q dot. Okay, and we'll borrow this idea for the quantum fields as well in the canonical quantizations. So whenever you are doing these canonical quantizations, effectively you are doing in terms of the from the concept of Hamiltonian, and Hamiltonian, they are independent. But later, when you talk about some kind of process calculation, scattering amplitudes, decay, and all those things, we will do in a Feynman diagrammatic method. And to do so, what we have to do, we have to extract the information of the Feynman rules, okay, from the Lagrangian. That's how we'll do that thing. So you can understand that we are doing the quantizations in terms of the Hamiltonian, but when we calculate something physical observables and so on, we are actually using the Lagrangian. That means there should be some kind of smooth transition from the Hamiltonians to the Lagrangian. Okay, and to do that, we have to import something called the time ordering, and there we'll see how the time ordered Hamiltonian is related to the time ordered Lagrangian. And as I said, that it is not obvious that they are just equal, right? Because of the reason that I told you, that the time ordering notions are different in Hamiltonian and in the Lagrangian. So once we able to understand how the time ordered Hamiltonian is related to a time ordered Lagrangian, then only we can use the quantization principles derived from the Hamiltonian and define our quantum theory, which we can describe later in terms of the Lagrangian. And then from the Lagrangian, we can define the action. Okay, and from that action, we should be able to calculate our Feynman rules. Okay, and propagators and all those things. Further, we can calculate the scatterings, amplitudes, decay width, cross sections, and different kind of. Okay, so yeah, so at this point, up to this part, if you have any question, please let me. Okay, so So now let's try to elaborate this equation of motions and these chemical things. So here, as I've mentioned, that this PR, which is your del L del QR dot, is basically your canonical conjugate momentum. This is the canonical conjugate momentum. Okay. And then we can define our Hamiltonian as, so this is exactly what you have done in classical mechanics also. Right? So this is the definition of my Hamiltonian. And then we can find out these equations of Pt as I is U. So now there's this few steps. I believe you should be able to do that, that you plug this H from here and you know the relations, the commutation relations between the QR dot, QR, PR. So if you do that, what you should be able to find out is that QR dot plus I sum over Pj UJ dot QR minus I L QR. And then if you have to calculate the L QR commutator, then you can write it down as a del L del QJ dot QR plus del L del QJ QR, right? And then it is basically nothing but my del L del QJ dot QR commutator. So if you do and put it back in the earlier equation, what you find out dqr dt equal to qr dot plus I sum over j pj minus del L del qj dot qr commutator. So now you can see that this equation holds as long as you are defining PR as your del L del QR dot. That is the one kind of equivalence, right? And similarly, you can calculate starting from the scratch. And this I'm assigning as a homework, especially I, H, PR is related as del L del QR plus I over J Pj minus del L del Qj dot PR. Okay. So finally, if you combine both the things, we get dpr dt minus del L del QR equal to ddt of del L del QR dot minus del L del QR equal to 0. So this tells you basically that the canonical equations are equivalent to your Lagrange's equations. Canonical equations are equivalent to Lagrange. Okay, and this is very fundamental fact for the quantizations. Okay, that means basically we can borrow this canonical commutation relation. So this is true only when the canonical commutation relations are home. The canonical commutations are satisfied. Okay. So now you can see there is a equivalence about the satisfying the canonical commutation relations and the canonical equations and the the Lagrange's equations. So that's how it allows us to define the equal time canonical commutation relations. Okay. So that's what you do in the quantum mechanics, right? And we'll see when you compute these canonical commutations in unequal times, okay, then that will lead to something very important in the context of quantum field theory. Okay. But here they are basically equal time commutator. So that's why I'm explicitly mentioning both as your P0 coordinate RS. Okay. And also if you define them in a different time, PS, T, they are also written as a delta RS. That means these equal time commutators are basically independent of time. This is very important. Now, so now we'll pay our direction to the quantizations of free fields. So now we consider for the quantizations, all these quantum fields are basically nothing but an accumulation of the infinite number of harmonic oscillators. So the advantage is that basically this, because all are basically, you know, nicely approximated harmonic oscillator, and we know how to quantize the harmonic oscillator, so we can borrow that idea to quantize our free fields. Okay. So let's consider the n systems. Okay. And such that the total Lagrangian, you can write it down as a n, and each has the channel momentum and the coordinates. So then the variation principle, V1, V2, ln equal to 0. Now, when this n is very large, very, very large, okay, then what will map this Qn as some phi of x, okay, and then Qn dot as my phi dot. And as I was telling earlier, so in the quantum field theory, we'll upgrade these JNS coordinates and the momentums as a quantum fields, which are basically now my operators. So then in this language, we can write it down as a so delta dt. We have this talk about, let's say, one dimension. So we have this dx, and this Lagrangian is now a function of these fields and its derivatives. And this will be 0. Now, as we have assumed our classical Lagrangian or the quantum mechanical Lagrangian to start with Q dot only, so that's why you have phi dot. But certainly this is not the generic one. We can have a higher derivative terms in the phi, and then automatically your Euler-Lagrangian equation will be modified. But for our present discussion, we will restrict ourselves for the just phi dot, single derivative on the phi. So now the whole thing was my Lagrangian. Then what about this part? This is my Lagrangian density. Because it's a one dimension, so I define that Lagrangian times this dx is basically my total Lagrangian. That's how I define the Lagrangian density here. So now, before proceeding further, let's assume that phi of x is real scalar field. So at this point, you can assume them to be the classical real scalar field until you define the quantize. Now, in quantum field theory and particle physics that we are interested in, so we have a very preferred unit system. Okay, and that's called the natural unit. It's very simple. As we consider h bar equal to c with the speed of light in a vacuum, it's basically 1 without any unit. And if you do so, what you can nicely construct that the dimension of mass, length, and time, they are now related to each other. And what is the relation? Your mass dimension is dictated by m, and then you have a length, and then you have a time, but they are not exactly equal, but they are inverse. And it is not very difficult to realize this thing, because you see, if you use this kind of relation, E equal to h nu, nu is the frequency, so hc by lambda, lambda is the wavelength having dimension of length, okay, and then E equal to, you have a mc square, right? So then you see that mass and length are inversely proportional to each other, okay, and then frequency, which is inverse in time, so that's why the time and length are equivalent, and that's inversely related with the mass. And this is what is actually makes sense, because the mass and energy, they are basically treated in the same footing. Okay. So if you increase your energy, okay, that will be decrease in your length. And that is what I expected, right? Because if you think how the microscope works, if you want to probe something in a smaller and smaller length scale, you need a higher frequency light to scatter, right? And that's what is actually, we are borrowing the idea for our high energy experiments also. If we want to see an atom, inside the atom, inside the proton, and so on, so you need to probe the smaller length scale with the higher energy. And that's what is actually conceptually you can relate with this one. That smaller length scale, that L is smaller, E is larger, right? So that's why this E inversely proportion of the length is basically is an artifact of the natural units, and that's what we see also, observe also this kind of phenomena. That if you have to probe smaller and smaller length scale of the high, and that's the name actually, the high energy physics. We talk about we declare ourselves a high energy physicist because we are working in a very smaller and smaller subatomic length scale. Okay. So now, if in this system, if we work like this, now we have to worry about what are the mass dimension of the fields and so on. So now if you remember how you define your action is I is h bar. Now as you know, in the exponential, these arguments are dimensionless. I have set h to be 1, so dimensionless. So automatically tells you that action, if you consider, that should not have any dimension. Right? Now, if it is so, if action is defined in this, then d dimension, if L is the Lagrangian density, then this is the measure or the volume element in the d dimension space, right? So then what we can say that these whole quantity is basically dimensionless. So then L will have a dimension of inverse L to the power minus D, but this is certainly M to the power D. This is very important. Okay, we will encounter and we'll use this thing again and again. So Lagrangian density has a mass dimension same as the space-time dimension we are working on. So in this course, we will be working with d equal to 3 plus 1 dimension to our Lagrangian density will have mass dimension 4. Okay. Up to this part, any question? So if you want, you can drop your questions in the chat box also. So then I can answer the immediate related question, or you can ask many other questions related to the subject, but I can answer them later. But if you have immediate questions on the ongoing discussion, you can immediately drop that question. Yes, sure. So what I was saying, that if you look at how the S matrix and all those things are related here, so because this is the how the you write down an unitary evolutions, right? If you remember in the quantum mechanics, the scattering and all those things, the S matrix appears through the unitary matrix in this particular form, e to the power is h bar, right? And then this is the same. It's nothing in quantum field theory so far. This is in the quantum mechanics. If you go back and you see how the S matrix is introduced and how an unitary operator is introduced in this particular form, that equivalence you write it down, right? And where you can show that S dagger S is equal to, you have to satisfy all those quantities. Right? So that's how you define this way. So now this H bar we are setting it to be 1. So the whole argument needs to be dimensionless. So S is also dimensionless, and that's m to the power 0. But action is basically the integral of the Lagrangian density. And how this density is coming? Because D have a spatial part and the temporal part, right? So you can think of S as dt and then dd minus 1 x. This is your total Lagrangian. So now I have combined this dt and dda. So that's what I have written it as a ddx. Okay. So now, so if the left hand side is dimensionless, so then whole combination should be dimensionless. So the dimension of this measure should be cancelled exactly by the dimension of the L. And that's how the ddx is basically what? It's a basically volume element in the d-dimensional space. But this volume element is nothing but you can think of L to the power d, because each side has a length dimension L1. So d will have a d copies of that, say L to the power d, right? So then this must have dimension L to the power minus d, such that as a combination, this whole quantity is dimensionless. And that's what I mentioned. Now L inverse is basically your, as I mentioned, L inverse is basically your M, right? So from there we can relate that okay, this L inverse D is basically M to the power T. So the Lagrangian density has a mass dimension of T. And because in our discussion is D equal to 3 plus 1 is a 4th dimension, so Lagrangian density will have a mass dimension 4. Okay. Yeah. Is it clear now? Okay. Very. So now, so we know what is the Lagrangian density of mass dimension. But then, whenever we will write down an explicit Lagrangian, okay, so we should be able to calculate the mass dimension of different quantum fields, and that will be very important. So we'll come back to this discussion later. So now, if we think about our relativistic framework, okay, so there, so what we do in the relativistic framework, we do not distinguish our space and time, or we do not treat them separately. Rather, we use space and time on the same footing, and that's why you can understand already I have included this dt and dd minus 1x to define the d-dimensional space-time measure. right? So now, so that's why this phi dot, which from the non-relativistic way I defined, and that was like del t of phi or ddt of phi. Okay, now we write down in a much more covariant form, which is basically my del mu phi. And here mu runs from 0, 1 to 0 is the temporal part, and 1, 2, 3 for the spatial part. So del mu has a time derivative as well as the Laplacian kind of derivative. Okay, the spatial gradient, you can think of that way. So then our Lagrangian is basically a function of phi and then del mu phi. Okay. So then if you perform the variation principle again over a manifold, so what will be before x, L phi of x, and then del mu phi. And this variation is basically 0. So again, if you find out the variation laws and all those things, you should be able to find out the Euler-Lagrangian equations in covariant form. Okay. So how to do that? So you take a variation. So variations will be now bounded before x. So now del phi alpha plus del of del mu phi alpha delta of del mu phi alpha 0. Right? So then the manifold has no boundary in which our quantum field theory is being built up. That manifold doesn't have any boundary. So that's why we can drop those surface terms for the bounded terms. And why that is important? Because if you think of this quantity, del mu phi, right? So this will be basically your some kind of a, let's say, this is not a field, but rather some kind of variable that you put a phi tilde. So from there, you can write down this is my boundary. So this I call that the sigma mu and the phi tilde mu, where this d sigma mu you can write down d mu d4 of x just by the partial derivative, or you can put a minus sign if you want to. Okay. But now, so that's why you see in this particular situation, when I have this Lagrangian, okay, in this particular form, and then I have another Lagrangian where the d mu of some quantity I have added. Now, as you know from the Gauss's theorem, if you perform this, you can write down the, remember the del dot A as a dot ds kind of integral from the volume integral and the surface integrals, how they are related, right? So there you find out that this is the total derivative term. So this term is total derivative term, right? Okay, so let me explain this manifold if someone asking. So what I was saying that the field theory that I'm describing here, basically in a manifold where there is no boundary. So if you do not have any boundary, so you do not really care about putting those boundary conditions, and that's why we can avoid any kind of contributions from, the manifold is basically, you can think of where the quantum field theory is basically being described here. like a field space. Okay, that's the manifold here. So now, if we had the total density terms in the Lagrangian, and then because it's inside the integral, if apart from the total density term as the integral, so what you'll get this contribution only. But if there's a boundary, so this kind of operators basically vanishes at the in asymptotics. Okay, so that's why they do not contribute. And that is one of the reasons for our construction that there's an equivalence of this Lagrangian. That means if you solve the Euler-Lagrangian equation, then you may not get unique Lagrangian. You may get different kind of Lagrangian. And one is differed from other by a total derivative term, right? So then if I have a Lagrangian L1, and then if I have a Lagrangian L2, which is basically L1 plus total derivative term, in our context, we'll consider L1 is equivalent to L2. Because the total derivative terms are not offering any kind of physical, quantity which can spoil your calculation or which can differ your calculation. So in the quantum field theory, what we are interested in a boundaryless manifold, the Lagrangians which are differed from each other by a total derivative term, they are equivalent. That is one of the important things that we need to remember. And also you can check explicitly if you add a total derivative term, then it will not modify your equation of motion as well. So if you use those things, then what you can write down the del L by del phi alpha minus del mu del L del of del mu phi alpha equal to 0. And that is our Euler-Lagrangian equation that we are interested in. Now, one of the quick cross check is if I give you a Lagrangian, which is the Klein-Gordon Lagrangian for real scalar field at minus half, then you write down del mu phi plus m square phi square. Okay. And then if you use this Euler-Lagrangian equation of motion, okay, so what you find out, then box minus m square acting on phi equal to 0, where box is defined as del mu. So that's how, for a given Lagrangian, we can calculate the equation of motion. And this is my Klein-Gordon equation, which we are familiar with. Right? So for any given Lagrangian, we should be able to do that thing. Okay. But remember, I can add a total derivative term, let's say del mu phi del mu phi. If I add this kind of total derivative term, then also you can cross check that your equation of motion will be still the Klein-Gordon equation of motion. Is the Klein-Gordon Lagrangian in the Euclidean sector? No, what do you mean by Euclidean sector? I have not defined the metric signature of del mu. So until I mention that explicitly, it is not needed at this point actually. Of course, you can write down in Euclidean your del mu, you can write down that way, but not needed at this particular point. So now, so this is how basically you define the this thing. And more important part that in the Lagrangian, you see the kinetic term is basically your phi dot square, right? So the sign and all those things in a consistent way we have to put such that when you calculate the Hamiltonian, that should be a positive definite. That is one of the important criteria. Okay. So you can cross check by doing that. You calculate the Hamiltonian, which is alpha d cube x pi alpha dot minus d cube x Lagrangian density, and which is basically your d cube x, the Hamiltonian density, right? And this Hamiltonian density you write then as a pi alpha dot minus Lagrangian, and if you calculate, you find out half of pi square plus gradient of phi whole square plus m square phi square, and it is greater than 0. Okay. So this is one way to cross check that aspect. That, I mean, they have the, like when you define the Lagrangian, they have the current right sign or not. Okay, fine. So now, if you want to write down this second quantizations in terms of the fields of this phi and all those things, so how to write down the equal time commutator? The equal time commutator, when I'm writing x0 equal to x0 prime, it's my equal time commutator, is basically given as now my phi alpha x, phi beta x prime is I delta alpha beta delta x minus x prime. Okay, so x0 equal to x0 prime is default. So this is the spatial vector you can write in electricity, but in a Cohen form, if you want to write down, then you write down a 4-dimensional delta function. Okay, but you can check that these are the phi alpha x, phi beta x prime, and then you have phi alpha x, phi beta x prime. These are basically 0, irrespective of the choice of your x and x prime. Okay, this is how you quantize the fields. Okay, yeah. Up to this part, any question? Okay. Now we'll make certain assumptions. To proceed further, we'll make the assumptions, and that's why it's very important to remember the assumptions then, and the theory that you are constructing, you know where they are applicable and where they are not. Okay, so alpha and beta, you can think of there are multiple scalar fields, for example, as a phi 1, phi 2, phi 3, and so on. Okay, so this alpha is like a, n number of scalar fields, so 1, 2, 2, certain n, alpha and beta both. Well, so I'll come back to this question later because I have not defined that thing. Okay. What is the fate of this thing? And this will be more important at this point. We just define in this particular way, but it will be more important when you talk about the unequal time commutator. At that time, and the simultaneous, no, this is like a simultaneity. You can think of like I'm assuming in the same time, t and t prime. Okay, but what you are asking about the space-like or time-like intervals and all those things, that will be more important when you talk about the unequal time commutator. Yeah. So what is the question? Can you explain how phi enters the Lagrangian as a function? Because phi, no, so then actually they are the functional, not the function. So more mathematical cards, they are functional, not the function. And when I'm talking about this, they are the basically local Lagrangian. Okay, maybe I was avoiding to mention those words as of now. So we are dealing with the local Lagrangian, right? So that's why in the Lagrangian, I'm assuming they have the only fields and its derivatives. That's what constitutes the Lagrangian. If you have derivatives separately and then you introduce your Lagrangian, that becomes a non-local Lagrangian. So that's a different way to deal with that. We talk about the local Lagrangian quantizations because that's how the we deal with it. Okay. Yeah. So that's why the Lagrangian is basically a function of your field and field derivative. Here the function phi of x and del phi by del x are del x are independent. Del phi and del x are independent. What do you mean by that? Can you elaborate? That's what I'm saying, that here the phi and del mu phi. These are the two quantities actually we are considering here. Okay. So now if you split this part, okay, so if you split this part, this will contain a del 0 phi, and then you have a gradient of phi, these two terms, right? No. So Lorentz invariance is a different thing. Don't, and let's try to be with the pace of the lecture. Don't to be, separately. Okay. So del 0 phi and gradient of phi. Now this del 0 phi is basically derived from phi, not this one. So that's why this is an independent quantity. Okay. So this, because it's an independent quantity, we can treat del mu phi as an independent quantity. That's the difference. Now, now we are not treating your dt and dx in a separate way. We are assuming the space Lorentz invariance such that everything is written in a coherent form. So that's why if you see now all the measure when I was writing earlier and the derivatives there basically in terms of the del mu. Okay, so that's how you write down in a coherent form automatically is a consistent way you can write down a Lorentz invariant way. And Lorentz invariant way is only the Lagrangian, is basically Lorentz invariant scalar. Okay, but you can have a quantities which are transformed in the Lorentz symmetries. So that's why Lorentz invariance is not the correct way to do that thing. It's called the coherent way. Okay. Any other question? If we add higher order of phi and this thing, and then can we take negative? No. If you take H, that's a lot of problems are there, because then it becomes basically unbounded from below. You do not have the vacuum and all those things. So that will be an inconsistency of our discussions. So that one has to be very careful about those things. If you have the higher order of phi, if you add, then basically, and if you make the coefficient to be negative, your potentials and all those things will be unbounded from below, and that we do not want, because your vacuum will start decaying. We don't want that thing at this point. So we have a free theory, okay, and then our kinetic term is basically positive. That's one. We do not want any kind of negative norm states and all those things. So if you have a negative energy and Hamilton is negative, then you have a negative norm states and all those things that we don't want at this point. Okay. Yeah. Any other question? Okay. So now coming back to what I was saying, that what are the assumptions we have to make? The first is the Lagrangian density is basically invariant under Lorentz transformations. Okay. So that means this is a Lorentz scalar. Okay. Second assumption is basically H computed H that you are computed from L is a positive definite. Okay. And third is basically the in case of non-interacting theory, these scalar, real scalar fields phi, they satisfy your plane Gordon equation. Okay. So now let's have a relook into that fact. So you have this del mu phi whole square plus m square phi square. So if you do suitable Lorentz transformation, this is a spin 0. So spin 0 object do not transform under the Lorentz transformation. And this m square is also invariant under the Lorentz transformation. So that this quantity Lorentz scalar. And you can check that del mu phi is transforming like a vector. So you have two vectors are there which are contracted. So that's why they make a Lorentz scalar out of that. And here we use this symbol sometimes I del mu or equivalence of p mu. So sometimes we write down this plane Gordon equation also in this p square plus m square acting on phi equal to 0. So this is the plane Gordon equation in the momentum space if you want to think about. Okay. Now for a real scalar field, only one kind of real scalar field we can have these relations, what I was writing for multiple fields, phi x prime equal to 0, irrespective of the choice of your x and y. Okay. And then we have this phi of x, and phi of x prime is I del cube x minus x prime, because it is an equal time commutator. So just to explicitly mention that x naught equal to x naught prime is already there. So I don't need to really mention that thing. Or if you want, you can mention del for by default. Okay. Fine. So then we'll try to find out. Now, as you know, that if we have to quantize some theory, we have to construct something and some manifold which is basically compact. Now, one nice example would be, for example, if you think of like a free particle, right? So free particle is flowing from minus infinity to plus infinity in the space, right? So that's why they are not trapped anywhere. So you can really quantize them. Okay. And the signature of the failing of the quantization is that the spectrum of the free particle is basically continuous. Okay? With energy, if you calculate, it is basically continuous. Right? But now, as you have learned already, one kind of quantization in the quantum mechanics is a particle in a box. So let's think about you have a one-dimensional box, right? And there, if you make the boundary walls and be very, very rigid, okay, that means their wave functions are basically, the particles is confined in this regime, and here there is no existence of this field or the wave functions, and then you have to put some kind of boundary conditions. So you can think of an infinite sized box, you are reducing and making it finite. Now you see there's a compact space, and compact space are actually some kind of boundaries. So you can put some kind of boundary conditions, and these boundary conditions when you impose, you make basically the spectrum discrete. So to understand these quantizations, we borrow the idea of this particle in a box. So what we assume that, okay, we have a volume of, let's say, order of L cube, okay, and there we impose some kind of periodic boundary conditions, periodic boundary conditions, okay, and so I expect this phi of x, which is nothing earlier was the free particle, and now are trapped in this thing. So still phi of x, the generic solution I can write down in this particular form, e to the power I px. Okay. But now, and if they are free particle, then this p is continuous. But once they are trapped within this box, they are quantized. And how do we know that thing? And if you calculate, you will find out they are of this particular form, where nj belongs to basically your positive integers. Okay. Yeah. Up to this part, any question? So no. So there are two things. So this is for the quantizations we are defining. The quantizations in the discretizations spectrum. So this is a quantization. But the field manifold, there's a field manifold is basically, there's no boundary. Or if you think about the boundaries are at the infinity where everything basically vanishes. Okay. So that's why These I'm talking about the wave functions. Right? No. So okay. So don't get carried away by this thing. So the fields are basically operator, but the functional dependence will come from the notion of the wave function. Okay. Now the wave functions are not the operators. So we'll see if we have to upgrade the quantum fields as an operator, then it is not only to the power IPX, but something more than that. So yeah, so stay with the pace. So now, if we have defined this field operator, so what we'll do, we define in this particular way. This is the P, it's the power IPX are basically my, the wave functional form, how the function dependence is there, and then there is kind of C, which is function of E and P. Okay. So this C are basically my operator value now. So this functional dependence comes from the free particle solutions, and by attaching a C, I say that phi is basically a field value now. So then it becomes a field operator. Okay. Then if you plug it back in your Klein-Gordon equation, okay. So what you find out, that C double dot T equal to minus P bar square M square P bar T. So P bar is basically like a variable, it's not a three vector, it's like a variable at this point, I think. Okay. So when it is a three vector, I will especially mention. So now when you identify that P0 equal to P bar square plus M square, okay, so then this is basically three vector. No, I think if we can avoid those junk mathematics words which you don't understand, it will be good. So C number, the commuting numbers and all those things. Okay, so that is not needed at this point because I have not defined the commutation in terms of C. So you do not know whether they are Gassman valued number or C number and all those things. Let's try to avoid those junk mathematical words. C is just an operator valued. No, that's all. So now this C, we'll write it down as C1 P bar e to the power minus I P naught T, and then C2 P bar e to the power I P naught T. And what is the reason of that? Remember, the fields are basically not only operator, but these operators are special operator. In what sense they are special? Because in quantum mechanics, when you define the operators, okay, there is a notion of, there is no notion of a creation of a field or something like that. But here we can think about creation of a field and annihilation of a field as well. And also because this P0 has both the positive and negative solutions are there. So that's why the notion of a particle and antiparticle is there. That means if you have a field, okay, so that field should carry the information about the creation and annihilation. And because we have this time translation symmetry and all those things, so we can identify an antiparticle as an conjugate of a particle. Now, why it is important? Because if a particle is flowing, let's say, minus infinity to plus infinity, this is an equivalent description of an antiparticle moving from plus infinity to minus infinity. Okay, so that's why when you define a field operator, so field operator should be able to encompass both the information that if this field is a creation operator. Like in harmonic oscillator, if you remember, there's a creation and annihilation operator. So the C are basically in the same way the fields are treated. So fields has a dependence, like field can evolve with time. So that's why the operator also. In that way, the C has a both momentum and time dependence. Actually, it can evolve with the time. Okay. And yeah, so this I'm writing in the momentum space. So now the field should have the equivalent description of when it can describe the creation of a particle. And as we know, the time translation symmetry and time reversal symmetry and all those things tells you that basically the equivalent description is basically anti-particle annihilation. So what we have is particle creation, and then there's a anti-particle annihilation. Both are basically equivalent. So a field operator should be able to describe both. So then if it has to describe both, it should have operator associated with both these phenomena. That means if a field is an annihilator operator, then it should have a particle annihilator and anti-particle creator. Or if a field is a creation operator, then it should describe the particle creation and anti-particle annihilation. And that's what we are going towards, that direction actually. So this field operator has these two components, and you can see they are associated with different energy signs. This is positive energy and this is a negative energy. But at this point, we do not know how these C1 and C2 are related to each other, if they are. In this description, we can write down our phi of x as 1 by 3 sum over p e to the power I p dot x C1 p bar e to the power minus I p dot p plus C2 p bar equal I p dot p. Okay. And then we can club these phases, and from there we can write down as over p as e to the power I p dot x C1 of p plus C2 of minus p e to the power minus I p dot x. Okay. So, okay, so let me describe that thing. How are the free field forms coming in the solutions of the field? Because they satisfy the free field equation with the Klein-Gordon. That's why. Okay, so let me describe this particle creator and annihilation. Annihilation. So what I'm saying, in quantum field theory, because of the symmetry that we have, like time reversal symmetry and CPT theorem and all those things, there's equivalence among this particle and this antiparticle. That if your particle is created and is propagating like this, equivalently you can assume the antiparticle is propagating in a backward direction. So then, when I'm saying a particle is annihilated, okay, so it has a two equivalent description. Either particle is annihilated or an antiparticle is created. For example, if I say that E minus is created, that automatically tells you that from vacuum that E plus has been annihilated and vice versa. So then if field you want to introduce as an operator, it should be able to encompass both the information, neither like bias to particle creation only or particle annihilation only, and it is not talking about anything about the antiparticle sector. So that's why this phi field have two parts, which are basically particle and the antiparticle. Okay, that's why the C1 and C2 with an integration. And now this field is written basically this to C1 and this thing, and then we identify for the real scalar field that C2 of minus P bar, we define it as a C1 dagger of P. Okay. So now in that language, if you write down phi of x as 1 by p over p, which is equal I p dot x C1 of p bar plus which is equal minus I px C2 dagger of p. Now you see, one is associated with this particle annihilation operator, and this is anti-particle creation operator, right? And that's what we expected. Now, if you use phi dagger, what you will get? You get C1 dagger and C2. So what does the C1 dagger will do? C1 dagger will create a particle and C2 will annihilate an antiparticle. But as you know, they are basically the same description what it is. So that's how you define these field operators in this particular form. And then from there we can define our momentum operators, canonical conjugate momentum operators, which are basically P minus I P naught to the power I P dot x C1 P bar plus I P naught to minus I P dot x C dagger P bar. And then we know the quantization relations between the phi and the pi, right? So if you use those canonical conjugate relations, then there's a homework that you can cross-check that C of P, C of Q, or the C dagger of P, C dagger of Q, then C 0, C of P bar, C dagger of Q bar, plus if you calculate C dagger of minus P bar, plus C of, sorry, C of minus Q equal to 0. Okay. And also you can check that C of P and C dagger of Q minus C dagger of minus Q, C of minus Q is equal to 1 by P naught delta PQ. Okay. So these are basically the relations, and also C of P, C dagger of Q is 1 by 2 P naught delta PQ. Okay. So now, yeah, so the question that you have asked, it should be clear from the canonical relations, because the P and Q are related by the Kronecker delta. So now you can understand whether they are different space, momentum space or something, or the same, right? So these are the basically fundamental relations that we have. So then if you want to write down your Hamiltonian, okay, or let's say now we use the normalized. So these are not normalized, so we have to normalize them. So I define the normalized operators in this particular form. So you have P as a 2 P naught A of P bar and C dagger of P as 1 by 2 P naught A dagger of P. So then we can get the relation A of P, A dagger of Q is delta PQ. So it is not that you are assuming in this particular case the compact manifold. So basically for the quantizations, you need to impose that thing. Otherwise, you don't get the quantizations. Yes. So the quantization is a you need to put the periodic boundary conditions. Otherwise, you do not have the quantizations. Yes. Okay. So now we can write down our Hamiltonian, which is basically d cube x Hamiltonian, which is half p naught a of p, a dagger of p, plus a dagger of p, a of p. And if we then write down this using this relation, what you find out that is a p naught, then a dagger of p, a of p plus half. But now you see, if you see that, as I told you, that basically fields are basically, we treat them as an infinite number harmonic oscillator, and that's what it brings in the picture. There's a similar Hamiltonian that you get, and this actually the infinite number of harmonic oscillators you are getting. But the problem is that for harmonic oscillator case, there's something called a 0-point energy, and the source of that 0-point energy is basically this half. But now if you have an infinite number harmonic oscillator, you can add this half infinite times and you get a very diverging quantity, right? And so that should not, but our quantity that will be computing in our field theory are basically all finite. So then what you do, you introduce something called the normal ordering. Okay, and this tells you that you normal order the operators in such a way that the annihilation operator is always in the right and the creation operator is always in the left. So then, instead of a total Hamiltonian, we will work with the normal ordered Hamiltonian, which I'm symbolizing like this, and which is nothing but my P naught A dagger P, A of P. That's all. So this is my normal ordered Hamiltonian. So this is very important in the context of your quantum field theory hypothesis. So we are working in a normal ordered quantum field theory. Okay. Yeah. Any question? Okay. So what I was saying that initially we said that okay, we have defined these quantum fields. It's kind of a mode expansions, and as you know, the small fluctuations or the expansion you can parameterize in terms of harmonic oscillators with a small amplitude fluctuations, right? So here, when we find the quantizations, then it naturally appears that the Hamiltonian looks like it's a sum of the infinite number of harmonic oscillators. So then each harmonic oscillator offers you this 0-point energy, right? But then if you have infinite number of harmonic oscillator, if you add up, then you get an infinite number of 0-point energy or the vacuum energy. And which is something very mischievous in a sense that in the quantum field, the quantity that we'll be computing are basically, the finite quantities, right? So one way to explain is that you can say, okay, and that you basically measure the difference between the energies and so on, but that's only for the energy. But if you later use this A and A dagger commutation relations and find out different kind of observables, you'll find out that unless you make the operators normal order, then you will be in some kind of trouble with the divergences. So that's why we introduce something, a prescription, which is called the normal ordering. And this prescription tells you that if you have the annihilation operator and the creation operator both, then you keep the annihilation operator on the right and creation operator in the left. And that's how we can avoid the emergence of this kind of divergences. And that's how the Hamiltonian that we'll be working with is my normal ordered Hamiltonian, and which is written in this particular form. Okay. So that is not a Dirac delta function is a defined in a continuous space, but now we are discretizing. So that's a Kronecker delta, right? So that is basically outcome of this Kronecker delta. This is not called the inherent inconsistencies. This is the way you have to define. So whenever there's a divergence in we encounter divergences, okay, so there's a prescription you have to propose. Okay, so this is one of the prescription of the normal order. So the quantum field theory that we talk about, the normal ordered way we have to define. So if you do not normal order, so that is basically your quantum field theory description is wrong. The prescription without normal ordering is basically wrong. It's not the, so you have to come up with a suitable prescription to recover that. Okay. For example, if we talk about the renormals and all those things, that's not a problem because the quantities we are going to compute the finite quantities. So whenever there's a kind of divergences, so we should be able to come up with a robust mechanism to do that. Okay, and then it should make our theory consistent. So that's the normal ordering. Similarly, later when we talk about the non-unequal time commutator, we'll see that there is something called a time ordering. Okay, so we have to deal with the operators that basically earlier operator, which is basically in time appears first, they should act because that's how it will be constructed. But yeah, we'll see that thing later, time ordering. But at this point, it's important that normal ordering. Okay, fine. So now this is how yeah. So if you guys want to do that, you feel free for the discussion. That's not an issue. Yeah. Okay. So now for the if we have so far we talk about the real scalar field. Now, if we want to deal with the complex scalar field, now what is the complex scalar field? That a complex scalar field has there's a two real degree of freedom where you write down phi as a 1 by root 2, phi 1 minus I phi 2, where phi 1 and phi 2 are real. Okay, and then define the phi dagger as 1 by root 2, phi 1 plus I phi 2. Okay. Then you have to define two canonical conjugate variables. One is phi dagger, which is del L by del phi dot, which is nothing but my phi dot dagger. And then we have to define phi, which is del L del phi dot dagger, which is basically my phi dot. And there we have the relation phi dagger. You can write down phi dagger, phi, and then that is my quantizations. Okay, and then my phi of x, if you perform the mode expansion, we'll find out this looks like a of p to the I p dot x plus b dagger. I'll explain these variables p dot x, and then phi dagger of x is basically now divided by 2 p naught b of p the phi p dot x plus a dagger of p is equal minus I p dot x in such a way that a p a dagger q equal to b of p dagger q is delta p2. So now you can see what is the difference here. And now instead of one scalar real scalar field, I have two real scalar field. So what I can do the whole analysis in terms of two real scalar field, or I can take a complex combination of them and I can define phi and phi dagger. Okay, but see the degrees of freedom should not change. So initially I have 2 degrees of freedom, so I have 2 scalar fields. So now we have a complex also, we have 2 degrees of freedom phi and phi dagger. And phi dagger is not the conjugate of phi, it's a different entity. That's how we have to treat. Then you define the canonical conjugate momentum corresponding to each field, and you define the quantizations. Now, when you have this mode expansion of the phi, now what you will have, it will have a linear combination of creation and annihilation, but now in a separate way. Because remember, phi dagger has a component of phi 1, and also phi has a component of phi 1, and similarly true for the phi 2, right? So that's how it will have 2 creation and 2 annihilation operator, one of the same kind A and A dagger, another would be the different similar kind among them but different than the earlier one, B and B dagger. So that's how the phi will contain A annihilation operator from phi, but it is equivalently contain an annihilation operator from the phi dagger. That's why it's like a B dagger kind of contribution. And phi dagger will have an annihilation operator of B and creation operator of the A dagger. Okay, so that's why this is slightly different than the earlier one, because now what you can do, you can write down in terms of phi 1 and phi 2, and then you will find out your phi 1 is described exactly in a similar way we define this thing. What does it mean? Your phi 1 will have A and A dagger, and phi 2 will have B and B dagger. But if you write down in terms of phi and phi dagger, you should be able to see this thing. That's one of the homework you can check, that I have given you this. So why don't you write down the expansion of phi 1 and phi 2 given these relations? And then you can convince yourself that, okay, the previous quantization that we have used, so that we can equally applicable here in this particular context as well. Okay, yeah, any question?